I am excited to introduce Dr. Daniel Whiter of AuroraZoo, who is a lecturer in space physics at the University of Southampton. And AuroraZoo is one of the Zooniverse projects. It's developed by the Space Environment Physics Group at University of Southampton. And whereas we ask you all to go out and observe auroras, with AuroraZoo, you look at pictures of auroras. And Dr. Whiter can talk a little bit more about that, but I'll turn it over to him now.
Yeah, thanks very much, and thanks for inviting me. It's really good to talk to you. Let me just try and share the screen. Does that work? Can you see the screen?
Mm-hmm.
Okay, great. Yeah, so thanks. I'm Dan Whiter from University of Southampton, and yeah, I'll be talking about AuroraZoo. So just a quick overview. I'll mention the instrument that we're using to record our images, and then why we needed to create AuroraZoo, then some technical aspects of the process of actually making the zoo and processing the data and so on, a bit about what the public does, and then briefly at the end I'll explain some other aspects of public engagement we do with AuroraZoo, and then plans for the future as well. So hopefully this doesn't take too long, but just shout at me if I end up talking too much. Okay, so firstly, ASK. This is a camera system called Auroral Structure and Kinetics, which is on Svalbard in the high Arctic. It's 78 degrees north, halfway between the top of Norway and the North Pole. Can you see my mouse pointer, by the way? Mm-hmm. Great, good. Yeah, so halfway between the top of Norway and the North Pole. It's three cameras which look at the same part of the sky. This is the ASK instrument on the side of a building up there on Svalbard. It has a box at the bottom where we have some computers, and then this structure on top, which we call the bucket. And you can take the sides off that, and inside it looks like this. So here's two of the cameras. These are not the sort of cameras you buy off the shelf. They're what we call electron multiplying CCDs, scientific cameras, and there's one on the other side as well. And then those have some lenses on top, which produce a 6-degree field of view. And each of those has a different color. Oops, sorry. Each of those has a different color filter on top. And then we can also fix these telescopes, which reduce the field of view down to 3 degrees. These filters, they're actually really narrow in wavelength. We look at very specific auroral emissions, and it's these three here. One from nitrogen molecules, one from O+ ions, and one from atomic oxygen. So we're cutting out almost all the light you see with your eyes. We don't look at the green or the red that you normally see. We're looking at these emissions because they're useful for the science we want to do, and they're quite easy for us to model with our computer model. Okay, and with these cameras, because they're so sensitive, even though we cut out most of the light, we can still run at 20 or 32 frames per second. So it's fast in aurora terms. This is just an example video to show you the kind of thing we see. This is an Allsky image. It's not the same time, it's just to show the scale. And this little blue box is the size of our field of view for the ASK camera system. This is false color from those three different cameras we put in the green, red and blue channels. But hopefully this is running okay over Zoom, and you just see how dynamic it is on small scales. And this is running at real time, hopefully view as well. So it's just a few second clip. It can be really crazy and dynamic on these small scales. So this one is, I don't know what's going on in there, these crazy small structures. I think this was 3 degrees field of view. So the really thin things in here are just a few tens of meters across, probably 100 kilometers altitude. So they're really small scale things going on in the aurora. Okay, so the point of ASK is to look at those small scale structures, and we're really trying to understand the processes which cause those features in the aurora, what causes the movement and the different shapes, and how the electrons which are producing those structures are accelerated down into the atmosphere. So ultimately how energy is transferred from space and the solar wind down into the atmosphere. And we also want to know what conditions are needed for those different types of small scale features, so that we might be able to forecast them better in the future and link them to heating of the atmosphere and so on. so we can understand what those different shapes and motions do once they're actually formed in the atmosphere, and what the electric fields associated with them do, and so on. So those are the overall science questions for the ASK instrument. The challenge is that we've got a lot of data. So now we've been operating for 15 years on Svalbard. This is a picture from our office, and these are all data tapes. They're LTO4 data tapes. Each one is 800 gigabytes, and we've got about 180 terabytes worth of data so far, I think, from those 15 years, because ASK is running automatically whenever it's dark. It has a light sensor and it just turns on, and we start recording. And we do throw away most of the cloudy data, so the stuff that's saved is almost all got Aurora in it, or Aurora within 20 minutes of the data. So it's just so much that we can't look through it on our own. We want to do large statistical studies, but we want to find the most interesting events to study. We're just not enough people to look through that, all of that. So that's why we came up with AuroraZoo, and we're inviting citizen scientists to help by looking at the images and the clips from ASK and classifying them into the different shapes and movements that we see in there, so that we can do those statistical studies and find the best events. So this is what the front page looks like. I'm going to show you in a moment what the process of classifying the Aurora looks like inside AuroraZoo, but it's up there at www.aurorazoo.org. So that's what it looks like. As Laura said, it's a Zooniverse project. Many of you, I guess, know about the Zooniverse, but just to give a brief introduction, it started with Galaxy Zoo at Oxford University, where they were asking the public to classify different shapes of galaxies, but now there's over 100 active projects. And actually, I took these stats from a few years ago, so there could be many more now. So there's quite a few projects looking at astronomy and space science, a lot of projects counting and identifying animals in camera traps, and things like transcribing old documents to generate weather records from ancient but very old records where people just wrote it down with a pen, things like that. So there's been an awful lot of measurements on these different projects and millions of registered users. So that's a lot of people that are willing to help out with the science. So then we thought, great, AuroraZoo is a good idea. We can invite people to help us classify the small scale aurora. We actually planned to start this a long time ago. So 2011, we first approached the Zooniverse about developing AuroraZoo, but they had a different model at that time. And at that time, we didn't have a grant to support the ASK camera system. We were between grants. And so they said, come back to us when we had funding, and then they would develop a project for us. In these years in between, I went away and lived in Finland for a few years and did a postdoc, and then came back to Southampton. And 2016, we were successful with a grant application. So we had money to run the ASK instrument again. And we went back to Zooniverse, but it turned out quite a lot had changed in that period. And they developed this project builder, which means we could essentially build the project ourselves. We didn't need them to do it for us. So that was great. So then I got some money to employ some undergraduate students over the summer, and they created the beta version of AuroraZoo in summer 2017 and 2018. And then we did quite a lot of testing. We took it to some events and showed it to the public, and they had a go at classifying the Aurora. And actually, we worked out that the original classification scheme we had wasn't really ideal. So in 2019, we redesigned it and updated classification scheme quite a lot, and then did a bit more testing, and then we finally launched just after the start of the pandemic last year. So it's almost 2 years since launch now. The first research paper using output from AuroraZoo was submitted December 2020 and published last year. And now today we've got over 363,000 classifications, and at the moment there's about 37,000 clips of Aurora in the AuroraZoo, which have been looked at by almost 10,000 people. So a lot of people have got involved and helped out, which we're of course really grateful for. Okay, just to show you what the project builder looks like. It's actually really easy to use. They have these different pages where you can just fill in the information, set up the project. So this is just the front page of the AuroraZoo project, where you can type in the text in a markup language. And here this was developing what I call a workflow, which is like the tasks which people do. This is all grayed out because it was live, so I couldn't edit it. But you can just go in there and you create questions for people to answer. So this was quite easy to use. Sometimes I find it's not quite as flexible as I would like, but generally it does everything you want. So that was really helpful, and we could make the AuroraZoo quite easily. Okay, so before the data goes into AuroraZoo, we do need to process it. This is a raw ask image. It's actually been scaled so we can look at it, because in reality it's 16-bit data. And a lot of people, when they look at that, they'll say that's really grainy or noisy, and it's black and white, not very pretty. Whereas this picture, which I took with my camera in Finnish Lapland, that looks really beautiful. So maybe they think we've got loads of bad data, but actually it's just because of the science we want to do with it. So as I said, we're throwing away most of the light. We're just looking at some specific emissions. We're looking at the really small scale stuff at high resolution. So this is the kind of data that's really good for our science. But to make it a bit prettier to look at, we do some processing. So we use this hue saturation value color system to make some color images. So you may be familiar with this. Hue is the color. Saturation is whether it's very gray or colorful. And then the value is how light it is, really, from black to white. And we take actually 4 images from Ask. So these are 2 images, consecutive images from one camera, and these are 2 from the other camera. I'll explain why we do that. First, we average together those 2 images. So here's an average of those 2. This one's an average of those 2. And that reduces the noise to, well, a little bit. It helps a bit. And then we take the Ask 1 image, and this brightness is proportional to the power of the aurora. Is the total energy flux of the electrons coming down to the atmosphere. So it's how the total amount of energy coming down. We put that in the value channel. It needs a bit of scaling because, as I said, this is 16-bit data and we need to scale it down to 8-bit. So we have an automatic system to do that. Then we take the ratio of Ask 3 and Ask 1. So we divide this image by this one. And the reason we do that is that ratio is proportional to the average energy of the electrons. So if the electrons are more energetic, we end up with a higher amount of Ask 1 relative to Ask 3. So we put that into the color channel, the hue. So we take that ratio image. It looks very noisy because both of these images are noisy. We convert it to a color using a color scale like this, and then we do some smoothing, use a median filter to make this smooth version and remove that noise. Then for the saturation, we take the Ask 1 image again. The brightest 0.5% of pixels, those are stars, and we want those to look white, because if they look colorful, people think there's aurora even when there's not. So we set those ones to have really low saturation so they come out white. And then also the dark areas, we set the saturation low so that looks dark as well, and it doesn't look like there's just very dim aurora there when there's actually not. So that's how we make the saturation image. And then when we combine the value, saturation, and hue, we get a colorful image like this, which looks a bit nicer than the original raw data. And it's easier to look at, it's easier to understand what's going on. And you can see the different color, which tells us about the energy. And then we put together a sequence of those images to make a 1-second clip. So here's
Could I ask a couple questions, possibly?
Sure. Yep.
Sorry to interrupt you. You actually have some good questions in the chat here. So
sorry, I didn't see that at the moment.
Yeah. But just to kind of go over again, you're not looking at the regular green and red lines, but just what lines are you looking at? And maybe just to abstract that into how the ratios of those colors indicate something about the precipitating particles. Yep, just to explain that a little more. So
these Ask 1 images, this is from N2. It's called the N2 first positive band, 673 nanometers. So it's in the red or near infrared. The N2 emission, that comes from mainly high energy electrons, but it's actually, the brightness doesn't change that much with the energy. It changes with the flux or the power coming down. rather than the peak energy. Ask3 is looking at an emission from atomic oxygen, 777.4 nanometers. So that's even further into the infrared. And that one comes from a mix of two different processes. There's one where you get electrons hit an atomic oxygen atom quite high up in the atmosphere, and that's low energy precipitation, because the higher the energy of the electrons, the deeper they penetrate down into the atmosphere. So the atomic oxygen emission, that comes from high up. You also get that emission from molecular oxygen, O2, which you get electron wax into the O2. It splits up into two atomic oxygens. One of them is in an excited state and produces that same wavelength. So that's sensitive to high energy precipitation. But this, yeah, I could have put a plot here actually. This one, as the energy increases, the brightness decreases. So by taking this ratio, that tells us the energy of the electrons coming down. So that was one of the reasons we have two different cameras looking at the same patch of sky, is because we can work out the energy of the electrons, which we can then use to understand more about the acceleration mechanisms and what's going on to produce the aurora. The second camera, which we don't include in AuroraZoo, is looking at an emission from O+, which is long-lived, which means it gets excited and then it takes on average 5 seconds before we get a photon of light. And it's from an O+ ion, which drifts in the plasma in the ionosphere. So you get an electron wax into an atomic oxygen, ionizes it to O+, it moves a bit horizontally, and then it emits 5 seconds later. And by looking at these emissions simultaneously, we can measure those drifts. There's a PhD student working on that at the moment. And if we measure the ion drifts, that tells us about the electric fields. So we can look at the electric fields around the structures in the aurora. So that's why we're looking at these emissions. The green emission has a lifetime of about 1 second, which means on small scales it gets all blurred out and we don't see this fast dynamic motion. So the green isn't really useful, and it's also difficult to model because we don't really understand the process producing that emission that well still, even though it's the brightest one. And the red line, that has an even longer lifetime, so it just completely smeared out on these scales. You don't see any structure at all, not really, not much. So that's why we're looking at these emissions.
And you're utilizing past research that correlated these two things to convert from the light into something about the precipitating particles.
Yeah,
And then you made it look kind of aurora-like again, right? Like, was that a deliberate choice to go with the greens, or because you could have chosen any colors, right?
Well, so actually the main reason we chose this color scale is because it's colorblind friendly, and the green and the red really isn't. And then we just, I don't know, we tried a few until we liked what we saw, I guess. It just looked quite nice. I guess it was a plan to have green as a fairly common color, just because that's what people expect the aurora to look like. They expect it to look green. Actually, as it happens, we have quite a lot of yellow in AuroraZoo, which we didn't really know before we processed all of the data. But yeah, that's where that color scale comes from. Originally, we did have a green and red one, and then one of the PhD students in the group was colorblind and said that's useless, so we changed.
Yeah, and does so Svalbard gets this kind of cusp aurora, right? Yep. Is that something that you're looking at in your data set, or?
Yeah, we see a lot of aurora around the cusp hours at midday. We do see aurora on the night side as well. From if it's very active and you have a substorm on the night side, the aurora oval expands up towards the pole, and we see dynamic aurora on the night side as well. A couple of years ago, a Japanese film crew went to Svalbard and they wanted to film aurora for 24 hours continuously, and they actually managed it, which we were all amazed about, because usually you get clouds or the ovals in the wrong place, but they actually had 24 hours continuous aurora. So yeah, you can see aurora all the time as well, really.
That's pretty cool. I'd like to give other folks a chance to ask their questions. If anybody wants to ask more questions at this point.
I just had a quick question about sorting out the data, did you manually go through all of the different nights and choose ones with Aurora, or did you also do the AuroraZoo to figure out which nights had Aurora versus clouds?
Yeah, that's a good question. So I did have something in here about that, and then I cut it out to save time, so maybe I shouldn't have done. But so there's two things. We do actually look at the data, quick look plots each night when it's running. We have what's, maybe you know what a Keygram is, I'm not sure, but it's like a 20-minute overview of what's in there. We have a quick look at all of those, and we delete the data which we know is definitely clouds. So that already gave us some idea of where the Aurora was, but still over 20 minutes, there could be a few minutes Aurora and then nothing else because our field of view is very small. So it's probably outside the field of view. So yeah, I also had an automatic algorithm which goes through and does an initial search for Aurora. It's just a brightness thresholding. So if the image is bright enough or structured enough, then we say there's probably Aurora there. Some of it is going to be cloud, but most of it is Aurora. Even once we've done that filtering, there's still too much data to look at, but we wanted to cut out all the boring stuff because otherwise people would just spend all their time looking at clouds or clear skies, and they'd get bored of that. So we wanted to make sure that most of the stuff in AuroraZoo is actually Aurora. So that, yeah, that works. There is a category in there which is no Aurora, so people can tell us that, but I think it's probably a few percent of no Aurora in there.
Thanks.
Okay. Anything else now, or should I continue and people can shout out when they have more questions? Okay.
Yeah.
Yep. Okay. Okay, so this was another example of this system of making a prettier or colourful clip. This one's a bit more crazy, whatever was going on in there. And then this one, we've got these curls in this clip. And you see that actually in this curl, it must be much more energetic because it's bluer, but then there's not much light around. So yeah, we end up making these nice clips like this. Okay, so then we put all this data into the AuroraZoo, and we asked people to have a look at those clips and tell us what shape the Aurora is, what movements happening, and then also how fuzzy or how diffuse the Aurora is. Originally, we didn't have this kind of classification scheme. We had a few classifications which were based on previous research into small scale Aurora and what type of things we expected to see. So one of them was curls. There's papers about curls. One of them was black Aurora, which we don't see very often in these clips. One was just diffuse Aurora, where it's just Aurora everywhere. But actually we realized that the classification scheme there was too tight. It didn't really allow people to properly classify the observations, and we weren't getting very good results. So after doing some testing and watching people doing the zoo, we changed the classification scheme and separated it out into the shape and the movement separately. So these are the shape classes we have in there. So there's 6 different types. There's single arc, which is just a nice band of Aurora. These are, on this scale, these are quite thin arcs. Sometimes you get 2 thin arcs right next to each other. And if you looked at this with your eyes or with a wide field of view camera or towards the horizon, it would probably just look like 1 arc. But when you look at the small scale shapes, it can be separated out into 2 arcs. This one is coronal rays, where you get these field lines. So I should have said that we're looking in magnetic zenith, which means we're looking almost straight up along the magnetic field line. So these rays are tracing out magnetic field lines just off the zenith, and it's like looking through a tunnel. Then we get Aurora everywhere, where it almost fills the field of view, or edge, where it partially fills the field of view. So it's not an arc, but there must be something going on outside the field of view. And actually, a lot of the time, these are probably what you would call arcs if you looked at it in an Allsky camera. But on our scales, we're looking within a broader arc. It could be patchy Aurora as well, pulsating Aurora, something like that. And then there's a category just for everything else really. When it doesn't fit these ones, it's irregular or blobby or patchy. So those are the different shape classifications we settled on. And it really was trial and error and just watching people looking at the clips and talking to them about what they saw, and ourselves as well looking through some of the data which we have been preparing for AuroraZoo. Then the movement classes. So there's drift, where it's just gradually moving at a fairly constant speed through the field of view. Curls, waves, and counter streaming, which we see quite often. So you get two regions which are flowing in opposite directions or at different speeds next to each other, and you get curls and things form on there. Then there's these ripples where you get rays which light up in turn or something like that. We call that ripples. And then these two are rarer and a bit more complicated. So we called those chocolate saws. We actually started calling this chocolate saws back in 2006 when we first saw it in Ask. And this one, we did a survey of a few people around the department, and the words which came up most common were psychedelic and kaleidoscope. So we called that one psychedelic kaleidoscope. And those two are the more dynamic motions. And this one, it's fairly constant brightness, but it's the structure itself is moving, and we think that looks like turbulence. We're not sure exactly where the turbulence is happening. There'll be a new PhD student starting actually who's going to look at that and try and work out where that turbulence is. This one is different because the structure isn't really moving that much. The structure is kind of fixed, and then you get the brightness flowing through the structure. So you get these kind of waves flowing through the pre-existing shape. I don't know what that is. It looks like some kind of wave process going on, but part of the point of AuroraZoo is to get some statistics on these and to try to learn what's making them. And then there's another class for just everything which doesn't fit the previous categories. And we don't get many of those, so I think the classification scheme does cover most things, which is what we wanted. And then finally, the fuzziness, or how diffuse it is. Sometimes we see these really sharp, clear structures, and other times it's very diffuse and fuzzy, and we don't really, you just see like a gradual change from bright aurora to nothing. And then sometimes it's somewhere in between, or it's a mixture where part of the aurora is sharper than the other part. So those are the four classes we had for the fuzziness. Okay, so this was a recording of me doing AuroraZoo, where actually it was just before it launched. So I had single arc and multiple arc completely separate, whereas now they're merged, and you choose later on if there's more than one arc or not. But this is how it works. So you get a clip of the aurora. It's 10 frames, so this is about 1 second long, and you can press play, and this slider means you can change the speed. And then first you choose what shapes you see, and then what movement. And on the movement, you can actually choose more than one, and then finally how fuzzy it is. So this one, for example, I could look at that. What did I choose? Probably edge or almost everywhere. Looks like almost everywhere for that one. And then the movement. So I went with drift, and that was it. So there's no right answer for these, and probably if I looked at it on a different day, I might choose something slightly different. But we have several people look at the same clip, and then we can average together their answers to work out what's going on. And there's a field guide in there which shows examples of these different types that you can look at, and if you need some help on those different classifications. And this needs some help, this task button also shows examples. Once you get near the end, you press done to move to the next one, but there's also this done and talk button, and if you press that one, it takes you to the forums which are attached to the project, and you can write a message about what you saw there, and we have a look at those. I must admit I have had not much time to pay attention to the forums for a while, which I feel a bit guilty about, but yeah, unfortunately there's teaching and everything else happens. But there's some very active users in there who are helpful and respond to questions, and have been gathering up different observations that people have made and comments they've made about different types of aurora. So that's how this works. Okay, so these are some results, some of the early results. So this is the different shape classifications. These plots are from a few months ago. So at this point, there was 2 or 3 months worth of data in the AuroraZoo, and these were the different types of shape classes we had. So fill, that's the Aurora almost everywhere, edge, single arc, flux, coronal rays, and irregular. And I made this bar chart or histogram showing when we saw these classifications at different times of day. So the overall shape is just when we saw Aurora on Svalbard. So we get a lot of Aurora around midday, and that's the cusp hours. And then in the early morning hours, and then this evening stuff, this is the more active Aurora when the Aurora overlooks expanded towards the pole, probably. It could also be transpolar arcs and polar cap Aurora, but that's probably the more active stuff. The reason that there's kind of these isolated spikes here is actually because we don't really have enough data in there yet. So it's probably still a few days worth of, or a few events which are biasing these statistics. Since I made this plot, I did put a couple more months worth of data in the zoo. So this is probably a bit smoother now. And the AuroraZoo is actually, they've just finished all the data a few days ago, and I'm processing the next batch to go in there as well. So as we put more data in, then we get a better idea of what we see. But we can already see some things. So for example, fill and edge, or at least fill is more common in the later hours, or proportionally more common. So that's the more active stuff. Single arcs and multiple arcs, they seem to be more common in the cusp and in the early morning hours. So that's when we're getting these thin arcs on small scales. And coronal rays, they're probably more common around midday. And then if we look at the movement, these are different movement types. So curls, for example, those seem to be more common in the midday and the early morning, but also there is curls in the evening as well. The more dynamic ones, the psychedelic and Chocolatosaurus, psychedelic in particular, that's definitely more common in the evening hours. So we're not expecting to see that really dynamic stuff in the cusp. So that tells us something about what's producing it. It must be connected to really active aurora on the night side. And then we can also separate it down. So this is all the different movement classifications when the shape was filled. So when we're looking at aurora, which is filling the field of view, we don't see, well, actually, we don't see much Chocolatosaurus at all, but we see a lot of psychedelic in the evening hours. So fill has a lot of psychedelic type, which makes sense. We don't see many ripples. We expect to see those mainly with coronal rays, so that's not that surprising. We do see quite a lot of drift and curls, so it must be some structure there which is just moving through, and the curls are forming within the larger stuff which is filling the field of view. So we need to look at these statistics in more detail. It's still early days of actually looking at the results from AuroraZoo, but as we get more classifications, we'll be able to do that. Other things we find are when people flag something up in the forums, which is just weird. It doesn't fit the classification scheme, for example, and this was one of those events. So this was a clip in AuroraZoo which a few people highlighted, and we realized this is something called fragmented aurora-like emissions. And I think you had a talk about this last year from Joshua Dreyer, who was working on these as well. But we found this event, or the citizen scientists found this event in the AuroraZoo, and we were able to look at that in a bit more detail. This is the Allsky field of view at the same time, and the white box there is showing the Allsky field of view. So here's these phase we saw coming through, and it's this bright green stuff, when actually the aurora was quite pinkish red color mainly, but this green stuff was these phase. And if I zoom in on one of those Allsky camera images and look at the Allsky image, you see this is the blob, which it looks like green in the Allsky camera image. And then with the Allsky we have a higher resolution, higher time resolution, and higher spatial resolution. And with the 3 cameras, we can measure the energies and so on. And we realize that this is actually not aurora. It's something, or it's not aurora caused by electrons coming down into the atmosphere. It's emissions caused by some other process, and we did some analysis on that. So here's a Keygram which is made from this cut. So it had a oddly positioned cut, but it meant we could look at the motion of this phase, and you see this kind of motion of the envelope structure, and then there's other motions inside it, and I can measure the speed of the motions in that way. And this was the first paper that got published, and there's a few people on there who were citizen scientists who found this event in the AuroraZoo and then looked at it a bit more with us. So we actually haven't published the statistics yet. That's the next step, but we published these phases which people found in the AuroraZoo. So we've now got a lot of classifications. One of the things we're planning to do is use machine learning to train the computer to do the classifications for us using the classifications that people have done themselves. And that will allow us to process a lot of data, including in real time. And so that will just increase the size of the statistical studies we can do. And then I showed you some initial statistics, but we need to dig into that a lot more and to understand what's causing those small scale shapes. I've also got plans to create new activities inside of AuroraZoo, like tracing out coronal waves to have a look at whether the center of them moves around and things like that. And I've got a new PhD student starting in September who's going to be really starting to take the lead on AuroraZoo, because unfortunately we haven't had time to really get the max out of it yet, I don't think. But he's going to be working on these statistical studies in machine learning and engaging with people in the forums and so on. So I think from September we're expecting a lot more results. Yeah, thanks very much. Hopefully that told you a lot of what you wanted to know, but I'm very, very happy to take more questions.
Very cool. Thank you so much. I like this compilation of all your clips here.
Different crazy things.
Yeah, those are the fun things. Yeah, I'll let folks ask questions. Jeremy, might you want to start us off? You had a few great questions in the chat and comments.
Oh, I think they were actually answered very well by Daniel. Is there a specific one that we could look at? I asked 3. One of them that I was kind of interested in is the idea of misclassification and the idea that in citizen science you have a core group of people that maybe do most of the contribution for classification, and then it kind of really tails off from there. So the 2 questions are, you know, what does contribution look like in terms of the community size and distribution? And then the other one is, can you get somebody who just sort of gets it in their head and starts misclassifying a bunch of stuff? And how do you account for somebody skewing the results because they might just see it differently than another person? Thanks.
Yeah, that's a difficult question. So we have at least 7 people classify each clip. In terms of the core group of users, if we have a look at the number of classifications by different users, there's probably, say, 100 people who have done hundreds of classifications each, and then it tails off, and you get people who do a few tens or just a few classifications. Because we average together classifications from different people, we're fairly confident that we're getting a good answer. I was going to say the right answer, but actually I don't think there is a right answer really, because it's different people look at it and have a slightly different idea of what's in there, which is fine, and I wouldn't say anybody is wrong. So by taking the consensus, then I think it's good. When we were testing, when I decided how many people needed to classify each clip, I took just 100 clips and put them in there and had people classify those, and then made a plot of the number of each type, each class that we had as we increased the number of people classifying. So if only one person classified each one, how many would we have of each type, up to if 7 people classified them. And after 7 or 8 people, the total number of each one didn't change very much, which told me that once we got to 7, that's enough. Going from 1 to 2 and 2 to 3, the numbers did change, but 7 seems really enough that we got good answers without wasting people's effort and having classifications when we didn't really need them. At some point, we added in data from the 3 degrees field of view when we had the telescopes on, and those were a bit harder to classify, so I increased the number up to 15 for those ones. But for the 6 degree field of view, it's about 7, 8, 9 is plenty. We've looked at weighting these for classifications as well, which is quite controversial in citizen science, I think, because people don't like the idea that their classifications count for less. But at the same time, some people who get very experienced do tend to have a better idea of what they see just because they've seen different types. So one of the weighting schemes we tried was that when somebody classifies a clip, if they agree with the previous classifications, they get slightly more weight and they get kind of a slight boost to their score. And we set it up so that their weight increases with a log scale. So to start off with, it increases faster and then it doesn't increase much anymore. And they never have a weight above 2, which means they will always be outweighed by 2 other people. And that seems to work well. This is all stuff we decide afterwards because we just take all the classifications and then we can process it and look at the weighting scheme. So it's something which the new PhD student is going to investigate whether it's actually needed and whether it helps or not. But I think we might do something like that so that the really experienced people, they can, if it's like a 50-50, then more experienced people will have a deciding vote, essentially, is how that would work. Does that answer the questions? Was there anything else?
Yeah, that's interesting.
That's really fascinating. It's like crafting a democracy in a way.
Exactly, yeah. We definitely don't want to weight people down because it's not good to waste people's time and have classifications which don't count. So everybody's counts, but if the more experienced users have the deciding vote, I think that's the best way to do it. So that's what we've been trying to do.
Any questions, folks we haven't heard from yet? Feel free, please.
I've got a question.
Awesome.
With the movement and structure that you've seen, have you ever noticed a twirling motion or structure that looks like 2 bands twirling? I know that when we take a long exposure of a Steve, it looks like 2 bands twirling, but I'm wondering about an auroral feature that looks like that.
Do you mean where you have, let me see if I can, maybe I don't have the best example in here, but so sometimes these curls, they sit in the same spot. So you get 2 regions which are flowing in opposite directions, and on the boundary you get this curling motion where they curl up. And sometimes you don't really see the join between the curls. Do I have another one in there? Maybe not.
Well, that could possibly be it. It's something that someone from Thompson has asked us to look for, and she sees it on a very occasionally, but
Okay.
I haven't seen it. And it's like 2 bands twirling together laterally.
Yeah, so I think on our scale sizes, they have to be quite small to see multiple ones, but you sometimes you do. And I've seen larger field of view videos, say 20 degrees or something, and you can have these really stable curl systems where it looks like Jupiter or something, where you have lots of curls in a long string, and then next to it more curls in a string, and they're just sitting there twirling around. So
that's,
maybe.
Yeah, that's not what I'm talking about. 2 long bands that are kind of twirling around each other. Not a curl,
right, I see what you mean.
Twirl, like 2 bands. Like when we take a long exposure of Steve, then it looks like it's 2 purple bands twisting and twirling around each other. But this is a different color that I'm looking for, green and purple. But
Donna,
anyhow.
Donna,
Yes.
I've pasted a link in the chat to an image. Does that describe what you're looking for?
Okay, I'll have a look. Thank you.
Let's see if I can open this as well. So I think it's that is actually something that some people in AuroraZoo thought they could see sometimes. I'm still undecided whether that's actually what's happening. Oh, yeah, okay, I just saw this image. Okay, so it looks like it's...
In the case of that image, I think in that image, we're looking at multiple vertical structures that seem to overlap. I don't know in that image if they're actually intertwining or if they just appear that way.
Yeah, it's... I don't know what the mechanism would be to create it.
Okay, thank you. I was just curious if you had seen it in the Aurora itself.
Yeah.
I know. Thanks, Chris, for the, and that is exactly what I'm talking about in the Steve, but I'm talking about in the main Aurora itself.
Yeah, I'm wondering if it's if there is a perspective effect, and whether if you're looking straight up, maybe you wouldn't see it if you're looking straight up if it's a vertical twisting, because we're looking in the magnetic zenith, so we don't see vertical structure really. We're seeing just horizontal structure, but that kind of twisting is. Yeah, I'd be curious if it's only seen, or if it changes if you're looking at different angles, and whether it's a perspective effect or whether it's actually something which is, or some different exposure times. Maybe it's because of some kind of movement. I'm not sure.
So I pasted another image in there that I think is a similar structure from a different night, but from a different perspective. That gives the view of the vertical structures that I think when they get more aligned, they create this illusion of an intertwining effect.
Yeah, I think
if you look at the tweet that Vince posted, that's what we're looking at.
Which one?
The one that Vince posted.
Oh.
He linked something in the chat.
Yeah. Oh, freeze. Yeah.
Yeah.
Oh, that. Yeah.
Yeah, that's what we're talking about.
Yeah. That's
Vince
that's
is a
very
real-time
different.
video of it too.
Yeah.
I have this just loading for me.
I have a question.
On the
the tweet might be more the kind of thing, the single arc doing something a little bit weird, but we really need, more statistics and when is it seen, but you're definitely seeing a lot of very, very small scale single arcs in your field of view. I don't know if you ever check if those are truly single arcs in the larger field of view.
I don't know if we've ever done that. I don't think so. I think sometimes you do get really thin arcs which are just on their own. But okay, this one in the top left, I wonder if it's something a bit like that on a larger scale. So this is, here we're looking straight up. So we see a kind of standing wave almost. I think it's probably formed in a similar way to the twirling curls, like this thing on the right.
Is there a bit of a Kelvin-Helmholtz effect going on there?
Yeah. I think that's what people think it is. Kelvin-Helmholtz sensibility causing this. Exactly where, I'm not sure. Whether it's in the auroral acceleration region quite close to the Earth, or whether it's far out somewhere, I don't think that's known. Or it might be in the equatorial plane somewhere. That's something we want to look at. But sometimes you do get ones which are, it kind of almost gets fixed, and it must be related to the speeds and things, I would have thought. And I wonder if that's what this twirling looks like if you see it from the right angle.
Jeremy, sorry, had a question about the difference between looking in detail at this wider view compared to the really fine scale structures that you're looking at. I'm not sure if I am doing justice to your question, Jeremy, but do you want to add anything more to that? They are different things. I mean, this is not necessarily like visible aurora. This is a kind of a different thing. I mean, it's infrared and it's false color, and it does have some really cool comparisons, but
yeah, I think there was this idea in the past about elementary aurora structures or something like that, where the larger auroral arcs are made up of these smaller scale things. I'm not sure how valid that idea is, but certainly when we look at aurora, we practically always see small scale structures in there. So there's definitely the stuff is definitely going on in there, but I think usually you either don't see it in pictures because the exposure time is too long, or you don't see it with your eyes because you don't look directly up where you see this. If you look side on, then this structure you don't see it, just gets the perspective means you're looking through it instead of up at it. So you need to be looking straight up at the magnetic zenith. So I think it's different processes, but it's related to the physics of what's causing the aurora. We see like wave motions and things like that, which is related to getting the electrons down into the atmosphere to make the aurora. So yeah, it's a different scale, which is telling you about different processes, I think.
Thank you.
Yeah, thank you so much. Do you have any questions for us? Does anybody else have more questions? Yeah, do you look at magnetometer data? That's a good question.
Yeah, we do. We tend to use magnetometer data mainly for context because the equivalent field of view of a magnetometer is huge. So it might tell us, oh, there's aurora nearby. So one of the statistical studies we want to do is look at whether the overall geomagnetic conditions and whether these different types of structures are related to different types of geomagnetic conditions, and then we'll be looking at magnetic indices to try to understand that rather than individual magnetometer data, I think. So yeah, we do use the magnetometers, but not to look at small scales directly.
I just looked at the time and somehow we've passed a whole hour here, but it's been really, really fascinating. I hope people go out and check out what's on the AuroraZoo. And if they have more questions, we can ask you more questions or email you or something like that.
Yeah, sure. Yeah.
Great.
Yeah, send me an email or a message on AuroraZoo as well. I can see those.
Okay.
So yeah, thanks very much.
Okay, well, good luck with the weather and the space weather. And maybe for this storm, it would be good to just try another citizen science project like AuroraZoo, since you guys are stuck at home, and encourage that for people now that you've heard about it and we've met Daniel. That would be an option. You'll get a spike of reports. That would be great, I'm sure. So,
yeah, thank you.
All right.
Thank you so much for being with us today, everybody, and particularly Daniel.
Yeah, thank you, everyone.
Thank you. Right.
Thank you, Daniel. That was fascinating.
Yep, thank you, Ray. Thank you.
Thank you.
Talk to you all soon. Thanks. Bye.